All right, welcome back, everyone. So, last time we really got into the weeds with deriving CAM profiles, right? We set up all those boundary conditions, solve systems of equations, and yeah, it's fundamental. You have to know it. But today, we're going to learn a much slicker way to do this. We're going to talk about the coordinate transformation method. So, think about it. That boundary condition method, it works, for sure. But you have to start from scratch for every single piece of the CAM's motion. A rise, new polynomial. A fall, another new polynomial. A more complex path? You get the idea. It gets really tedious fast. The technique we're going to cover today, it's a game changer. It's powerful, it's reusable, and honestly, it's just going to make your life a whole lot easier. Okay, so here's the plan. First, we'll talk about why this is such a smarter way to design. Then, we'll introduce this idea of a universal building block, one function to rule them all. After that, we'll build our transformation toolkit. We'll see how to build a return motion, how to connect different dwells, and then we'll wrap it all up by talking about your new design superpower. So let's jump right in. What is the big idea behind this method? Well, it's really a shift in how you think about the problem. Instead of reinventing the wheel for every single motion segment, we're going to take one single function and learn how to reuse it and modify it for everything we need. And this really gets to the heart of it. On the left, you've got the old way, the boundary condition method. You're rederiving equations over and over and over. It's repetitive, it's a ton of work. But on the right, that's where we're headed, the coordinate transformation method. We're going to have one pre-derived function, our standard function, and just reuse it for everything. It's elegant, it's efficient, and honestly, you're way less likely to make a simple algebra mistake. Okay, so this brings us to the core concept, the secret sauce, if you will, the universal building block. Think of it like a Lego brick. Instead of having a million custom-made pieces, we're going to start with one perfect standard brick that we can use to build anything. And here it is. We call it the standard rise function. So what is it? It's just a pre-made mathematical function that describes a super simple motion, a rise from zero displacement up to some total lift. Let's call it L. And it happens over a certain CAM angle, which we'll call beta. This one function, this is going to be our starting point for everything. Now, you could actually use this method with different functions, like simple harmonic motion, but for our main example, we're going to use the cycloidal rise function. And there's a really good reason for this. Its dynamic properties are just fantastic. It starts and ends with zero velocity and zero acceleration. Why does that matter? It means super smooth transitions between motions. In real high-speed machines, that's absolutely crucial for cutting down on vibration and wear and tear. So yeah, this equation looks a little complicated, but here's the good news. This is the only complicated equation you need to worry about. Everything else we do today is just going to be simple algebra applied to this one function. All right, so we've got our Lego brick, our standard function. Now, what can we do with it? How do we actually build stuff? Well, for that, we need a toolkit. And you're going to love this. It only has 3 simple tools. So here they are, our 3 basic moves. First, the angular shift. This just lets us slide the motion left and right along the timeline, the theta axis. Second, inversion. This is how we flip a rise upside down to make it a fall. And third, the vertical shift. This lets us move the whole motion up or down on the y-axis. That's it. Let's break down each one. Okay, first tool, the angular shift. This is all about timing. See, our standard function always assumes the motion starts at a CAM angle of 0. But what if you don't want it to start there? What if your rise needs to kick in at, say, 120 degrees? No problem. You just go into the standard equation, and everywhere you see a theta, you just replace it with theta minus 120. That's it. It literally just slides the whole curve over to start right where you need it. Next up, inversion. This one is super clever. Our building block is a rise function, right? It goes from 0 up to L. But what about a return, a fall? How do we get that? It's so simple. You just take the total lift, L, and subtract the standard rise function from it. Think about it. As the standard function goes from 0 up to L, the expression L minus y rise will go from L down to 0. Boom. You've just created a perfect return motion. And notice, we didn't have to do any calculus or solve any new boundary conditions. It's just simple subtraction. And the final tool in our kit, the vertical shift. So far, we've assumed everything starts at 0 displacement. But what if it doesn't? What if you have a dwell at some height, let's call it L1, and you need to rise from there to a higher dwell at L2? Easy. You just take your rise function and add L1 to the whole thing. It just lifts the entire curve up so it starts and ends at the right heights. Simple as that. Okay, theory time is over. We have our building block, we have our 3 tools. Let's actually build something. We're going to create a complete return segment. And here's the challenge. We are not allowed to solve a single boundary condition. Let's do it. So here's our mission. We need to come up with the equation for cycloidal return. It has to start at the full lift, L, and end at 0, and it can't start at theta equals 0. It has to start at some specific angle, we'll call it theta start. And the whole thing takes place over an angle of beta. So how do we piece this together using just our standard rise function and our new toolkit? It's just 2 simple steps. First things first, we need a return, not a rise. So what tool do we use? Inversion. We take our standard function and calculate L minus y underscore stand. That flips the curve upside down. Okay, step 1 done. But now that flipped curve is still starting at theta equals 0. We need it to start at theta start. So step 2, apply the angular shift. Everywhere we see theta, we replace it with theta minus theta start. That's it. And voila, here's the final equation. This function perfectly describes our cycloidal return, starting and ending exactly where we wanted it to. And I really want to drive this point home. We did not derive this from scratch. We didn't solve 4 equations with 4 unknowns. We built it. We constructed it by applying 2 simple rules to our standard building block. That is the entire philosophy behind this method. It's construction, not derivation. Okay, that was cool, but let's take it up a notch. Let's tackle a more complex and, frankly, a more realistic scenario that really shows off how flexible this method is. What happens when you need to connect 2 dwells that are floating? You know, not at 0 and not at the full lift. This table breaks it down perfectly. Let's look at the first case, rising to a higher dwell. So you're starting at some height L1, and you need to rise up to L2. First, what's the actual distance you're moving? That's just delta L, or L2 minus L1. So you take your standard rise function, but instead of using the total lift L, you scale it by this new lift, delta L. Then, since you started at L1, you just add L1 to the whole thing to shift it up. Done! Now for the return, say from L2 down to L1. It's almost the same logic. The distance you're falling is still delta L, so you use delta L in your inversion formula, and then, again, you shift the whole thing up by the starting height, which in this case is L1. See how we're just combining the tools? Okay, let's wrap this all up. What we've really done today is give you a new design superpower. You've learned how to stop thinking about CAM design as this long, painful series of derivations and start thinking about it like a creative, logical assembly process. So here it is, the cheat sheet. This is what you need to remember. You need to create a return? Just use inversion, L minus y. You need to shift the start time? Use an angular shift, theta minus theta start. You need to shift the starting height? Use a vertical shift, L1 plus y. And the most important part? You can combine all of these. You can mix and match them to build literally any segment you need, all from that one standard function. And because you're just manipulating that original function, you keep all of its great dynamic properties, like that 0 acceleration at the ends. So I'll leave you with this question to think about. This isn't just a math trick to save you some time on homework. It's a whole new way to think about designing motion. Now that you know how to shift, flip, and scale a motion with a few simple rules, just imagine the complex, multi-stage mechanisms you can now design and how much more efficiently you can do it. That's the real power you've unlocked today.